Good morning. Thank you for giving us the opportunity to share our research using CFD modeling and deep learning to aid the pulmonary disease diagnosis, specifically on detecting the obstructions in lower airway. First, I would like to thank all the co-authors who contributed to this research. We are motivated by the fact that occupational exposure leads to lower lung diseases with airway obstructions. Existing diagnostic methods are not very effective to detect those obstructions at their early stage. So we think that if we can use the expiratory airflow velocity in the chest as a biomarker to differentiate healthy lung from obstructed lung, then we can further do something or design some algorithm using the machine learning or deep learning to make a more effective diagnosis just based on the scanning of the airflow pattern, which is non-invasive. So this is the preliminary results we tested many years ago. So as you may see, we artificially obstructed some lung airways, and we do see that the airflow distribution in the chest are very different from each other. So we were thinking that if we can capture this airflow velocity pattern shift in the trachea, then we can use that as the information or as the input to the algorithm to identify where is the obstruction. We also think about the pathway to achieve this in clinical practice. Fortunately, we know there is kind of apparatus called hyperpolarized MRI, which will be able to scan the airflow velocity distribution in the trachea. Therefore, we propose a modeling framework to use our computational fluid dynamics to do the airflow simulation in the lung airway with and without obstructions. And we artificially create many cases with different obstruction sites. Using those contours as the input, we want to train and test our convolutional neural network to see how efficient they can be used to find the obstruction location in the lung airway. So, of course, for this kind of training and testing, the first step is always the preparation of training and testing database. For this study, the training and testing database are those airflow velocity magnitude contours with different obstruction locations, and all those contours were taken at a designated cross-section in the trachea. We selected one subject-specific airway geometry, and we generated the polyhedral mesh with near-wall prism layers. So for all the simulations, expiratory flow rate is 60 liters per minute. This airway contains 44 small airway terminals. So when we try to create different obstruction cases, we block one or two of those small airway terminals, which give us 990 cases, so with different obstruction sites. And so you may see the structure in this slide. And by saying that, after we finish all the simulations, we actually have 990 velocity contours labeled by their obstruction sites. So we divided those contours or those data by using 80% of them for training and 20% of them for testing. And of course, when we do the simulations, it's just classical computational fluid dynamics used in the long aerosol dynamics simulations. And I just listed some of the equations, but I will not have the time to go into details about those equations. And after we have everything, the database is ready. The second step, of course, is the training and testing of the CNN, which is the convolutional neural network based model. So we actually choose two different CNN codes available online. So one is called ULO v4. As you may see that this is the training process. So we have all the labeled contours goes into the system. And then we'll see that whether this model can be trained well to classify if the obstruction is in the left lung or in the right lung or in both lungs. And we also used another open source code, CNN code, which is called ResNet 50. And the idea is the same. So we input images as the label data, and we try to see how well that this algorithm can predict the obstruction sites. So here is the statistics. What we can see is that the average precision is pretty good, and all three tests we run using different codes give us the average precisions all higher than 93%, so which is pretty accurate. So the previous research results shows that those two CNN algorithms are able to capture the obstruction locations very well by classifying them into three categories. But do we really need to include a CNN-based model to do this kind of diagnosis? To address such a question, we visualized velocity contours in those cases with different obstruction locations. As you may see, using human eyes, it is really hard for us to directly tell the pattern shifts when we have different lung obstruction locations. So in that case, it gives us a hint that using the deep learning algorithms is necessary to achieve such a early obstruction detection diagnosis. We also compare the velocity profiles along two different lines on that cross section we selected in the trachea. This is like from the left to right line. As you may see, all those velocity profiles, they have no big differences among different obstruction locations. This is the comparison for the velocity profile along the line from the front to the back of the chest. And same conclusion can be drawn. There's no significant differences among those cases with left lung obstructed, right lung obstructed, or both lung obstructed. So in conclusion, we tested two CNN-based models to detect small airway obstruction locations, and the accuracy is pretty good, which are higher than 93%. And we also confirmed that the airflow pattern shifts among those different obstruction cases were not able to be identified directly using human eye. For future work, we would like to involve more subject-specific airway configurations to address the subject variability. Also, we want to add noises into our CFD contours to mimic the MRI image quality, which could be used in clinical practice. Also, we want to refine the algorithm to not only detect the obstruction locations in left or right or both lungs, but also to be more specific, which in the future we hope the algorithms can tell us in which lung lobe and in which generation are those obstructions located at. So that's all. Thank you so much. Please feel free to ask any questions.